Good afternoon, everyone. I'm Daniel Lidar of the University of Southern California. I'm the current chair of GQI, the APS topical group on quantum information, and I'm also the warm-up band for this rock concert. I'm deeply honored to have the opportunity to chair this special Nobel session, particularly because the Nobel Physics Prize this year recognizes two individuals who, through their research in manipulating photons and ions, have laid the groundwork for quantum information science and the possible realization of quantum computation in the future. They are Serge Haroche and David Wineland, who shared the 2012 Nobel Prize in Physics. Their citation reads, "For groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems." Like many others, I've been inspired by the works of Professor Haroche and Wineland to think about the control of complex quantum systems and the meaning of the measurement of an individual atom or photon. The work of Haroche and Wineland was in large part the driving force behind the establishment about a decade ago of the topical group on quantum information, GQI, which is now the largest and fastest growing of the 12 topical groups of the APS. GQI's largest growth sector is graduate students who are undoubtedly fascinated by the possibility of studying and building quantum information processing devices that operate on and take advantage of the laws of quantum mechanics. The potential of such information processing to outperform its classical counterpart is entirely dependent upon our ability to control and measure individual quantum systems. The 2012 Nobel Prize in Physics recognizes the groundbreaking research and discoveries that may make such quantum information processing possible on a large scale in the future. Of course, the ramifications of the research of Professors Haroche and Wineland extends far beyond information processing, as they are certain to explain in their lectures. Before I introduce our first speaker, I would like to draw your attention to a distinguished guest, His Excellency the French Ambassador François Delattre. He will deliver brief remarks at the end of the talks and before the beginning of the reception. It is now my distinct pleasure to introduce our first speaker, Serge Haroche, of the Collège de France and the École Normale Supérieure in Paris. He was born in 1944 in Casablanca, Morocco, and moved to France at the age of 12. Among his many awards prior to the Nobel Prize, he received the 1988 Einstein Prize for Laser Science, the 1993 Michelson Medal, the 2007 Towns Award, and the 2009 CNRS Gold Medal. The title of his talk today is Controlling Photons in a Box and Exploring the Quantum to Classical Boundary. Please welcome Serge Haroche.
Thank you very much for this very kind introduction. I feel deeply, I think we have to switch off this. I am deeply honored to have this opportunity to address the APS meeting, which is certainly the most important and the largest physics meeting in the world. So it's a great honor for me to have this opportunity to talk about the research which has led to last year's Nobel Prize. I will be talking about experimental quantum physics and start by a few remarks about quantum theory. As we all know, quantum theory has revealed to us a world where the concepts of matter, particle, and waves are complementary. Light, which is usually assumed to be an electromagnetic wave, is also made of discrete quanta, the photons, and atoms, which are generally considered to be discrete entities, also can act as waves, matter waves. And this duality has led to the superposition principle, to the idea, to the concept that system made of atoms, of photons, can exist in different states at once, so to speak, suspended between different classical realities, which is very difficult to understand, which is very counterintuitive to classical mind. If you want to observe this, you have really to in order to observe these strange properties, you have to isolate the quantum system from their environment, because due to decoherence, these superposition features are very easily blurred and disappear. The founding fathers of quantum theory had understood that, and they performed experiments in which single particles were manipulated, but of course these were thought experiments. They were virtual experiments, and you see here, for instance, the famous photon box that Bohr drew during his discussion with Einstein. I don't want to discuss in details the reason why they designed this experiment, but it was to study some basic concepts of quantum physics. And I draw your attention to the fact that you have a box and you have also a clock, which is an important part of the apparatus. And we will come back to this combination between a photon box and a clock later on in the talk. But at the time they were imagining this kind of experiments, they believed that this experiment will never be possible in the laboratory. Schrödinger also believed that. Of course, they knew that single particles could be observed. In fact, in the 1950s, you already had bubble chambers and the accelerator physics was starting. But as Schrödinger put it, it was quite different. It was observing particles after they had been destroyed. In a cloud chamber, you see the tracks of particles which have disappeared, and in accelerators, you see the debris of very energetic collisions. So it was, as Schrödinger said, post-mortem physics. And he wrote a very famous sentence: "It is fair to state that we are not experimenting with single particles any more than we can raise ichthyosauria in the zoo. We are scrutinizing records of events long after they have happened." In fact, things have changed since this time, and now thought experiments which control a large class of particles have become possible. Many laboratories in the world are manipulating single quantum objects made of atoms or photons and using these to develop experiments in the field of quantum information, trying to demonstrate basic effects of quantum physics and also maybe to harness this quantum logic to do useful things. The Nobel Prize has recognized this kind of research this year by awarding the prize to David Wyman and myself, but I think Dave agrees with me that we are just representing a wide community of physicists doing experiments, very beautiful experiments of various kinds. And we have been picked in this group because we have been working for a very long time. So this is the advantage of old age. We started doing this physics about in the 1960s or early 70s. I think Dave will tell you his part of the story, and I will tell you mine, which has started very long ago. The reason why this experiment had become possible is that because we have now new tools which did not exist at the time of Einstein and Bohr, tunable lasers which allow us to manipulate atomic systems with exquisite precision, fast computers which can detect and control the systems at a very fast pace and accumulate data and react back on the system, and also in some cases superconducting materials like the cavities that we use for our photons. So this has made this experiment possible, and the experiments that Dave is doing in Boulder and the ones that we are doing in Paris are quite complementary. What he does is to manipulate single charged atoms, ions, using lasers to control them and to observe their evolution. And in Paris, we do the opposite. We trap photons in a box, and we use a beam of atoms to control the photons and to observe and detect them. In both cases, we are doing what we like to call in vivo physics. We are trying not to destroy the systems that we are observing, and we are exploiting in various ways the interaction of matter with light at the most basic level. Fundamentally, at the heart of this experiment are the interaction of single atoms with single photons. So I will tell you now a little bit how all this started in my case. I have to come back to my thesis work, which was done under the supervision of Claude Cohen-Tanucci at École Normale Supérieure. At that time, at the end of the 1960s, I learned how to perform optical pumping experiments. In optical pumping, we use light to manipulate the magnetic moments of atoms. And so I learned that light was not only useful as a spectroscopic tool, as it had been for centuries, but it was also useful to manipulate matter. And this idea has become very fruitful in the years after that for laser cooling and all kinds of experiments. So we had atoms which had magnetic moments, and using laser light, we were orienting the magnetic moments and looking at the dance of these magnetic moments in radio frequency fields. And in order to understand the experiment, we developed the dressed atom formalism, which consists in dealing with the photons which surround the atom as part of the system and looking at the properties of the combined system atom interacting with photons. This is a picture which is imported from quantum electrodynamics, but it was quite new in atomic physics. And in fact, it was new because it's not necessary. Since we are dealing with huge amounts of photons, a classical description of the field is okay. Still, the dressed atom point of view turned out to be very interesting because it gave a synthetic view of the processes and allowed us to understand a lot of phenomena which were not so clear with a classical picture. But it gave to me the idea that the fundamental interactions of atoms with photons was this central in atomic physics, and the challenging idea of going down to a very small number of particles to the point where the quantization of the field would become not only convenient but necessary started to become pregnant for me. But of course at that time I did not know at all how we could achieve that. Then I left for my postdoc with Arthur Chalot at Stanford, and then I got acquainted with the first tunable lasers. In fact, the experiments I was doing before were done with classical spectral lamps, and then the lasers appeared on the market. And of course, this has been the big revolution in atomic physics and in optics. At that time, the tunable lasers were still rather crude, but we used pulse lasers to excite quantum bits in atoms. The idea was to start from the ground state and with a pulse of light to prepare superposition of states, and this superposition were evolving, giving rise to quantum bits in the fluorescence light. These quantum bits were linked to superposition of state, to quantum interferences, and they happened within each atom. In spite of the fact that we were observing billions of atoms at a time, the fundamental effect was a single atom effect. I just want to acknowledge the importance of these two people, Claude Cohen-Tanucci and Arthur Chalot, in my formative years. And of course, we all know that they both got a Nobel Prize, Claude Cohen-Tanucci for cold atom physics and Art Chalot for high resolution laser spectroscopy. But the story really started when I came back to Paris after my postdoc, and I started to use lasers to excite and to study Rydberg states. In fact, tunable lasers were the only possibility to excite with precision atomic levels near to the ionization limit, and it opened a terra incognita of a lot of levels which were very exciting to study because they had very exotic properties. They were very weakly bound, they were very strongly coupled to microwaves and to electric and magnetic fields. And we started in Paris to do microwave experiments. You see here the setup that we are using, which was quite simple in its principle. We have the atomic beam. The beam is intersected by lasers, which prepare Rydberg atoms. And then the Rydberg atom drift out of the interaction region, and they enter between two condenser plates where you apply an electric field. This field increases linearly with time, and it reaches at different times the threshold for ionizing two levels. So if you want to see a transition between these levels, you get a time-resolved signal, which is very handy and useful for that. And in fact, this is a detection technique that we have been using since then. The microwave was produced in a cavity made of two copper mirrors, and we were looking at microwave transitions. And we realized one day, at first with surprise, and then we understood what was going on, that if we started from the upper state of the atomic transition, you see here the ionization signals when the cavity, what we observed that you don't need to apply microwaves. if you start with the atom in the excited state and you tune the cavity in resonance with the transition, you see that the atoms spontaneously fall to the lower state, emitting their own microwave radiation. This is, of course, a maser, in this case from the 27 to the 26p state of sodium. But what was very surprising is that the threshold of this maser was exceedingly low. Whereas usual maser or laser system require billions of atoms, here we had a maser which was working with only 200 atoms in the cavity. And this is, of course, due to the very strong coupling of these Rydberg atoms to microwaves. So at the end of the paper, we said that if we could increase a little bit the Q of the cavity, we would reach a regime where we would have modified the spontaneous emission of a single atom. We are going to very small atoms, and this was a starting for us for cavity quantum electrodynamics experiments. So we immediately, to improve the Q of the cavities, there was a very simple thing to do, to go from copper to superconducting material. And we built a niobium cavity, and a couple of years later, with this niobium cavity, we were able to observe this effect with a single atom. We sent atoms one by one, and we saw that the transfer of the atom from the upper to the lower state was accelerated when the cavity was tuned on resonance. And we recognized that this was the limit of a maser when you reach a threshold with a single atom. But still, we were not quite satisfied. We noticed at that point that if we could still increase by 1 order of magnitude the quality factor, we would get to the point where the photon, which would be emitted in the cavity, would stay long enough for the atom to be able to reabsorb it, and we would have a kind of reversible exchange of a single atom with one photon. This is called the strong coupling regime of cavity QED, and it became really our obsessive goal. We wanted to reach this regime by improving the cavity Q. I show you here a few pictures which are taken in the lab at that time. This is me with my first two graduate students, Michel Gross and Claude Fabre. You see here Philippe Gouard. Philippe Gouard is a specialist of microwave technology, and we are very happy, very lucky to have him working with us at that time, because he was delivering all the microwave frequency we needed for these experiments, and he has started a company which is delivering microwave equipment to many labs in the world and have been working with us for a very long time. And in the last picture, you see again Claude Fabre, Yves Caluzny, and on the right of the picture, you see Jean-Michel Raymond, who was then my student and who has stayed in the group and who is now co-leading the group with me and with Michel Boyne, who joined us later. So it was a very exciting time in the lab, and we really wanted to achieve this strong coupling regime, and I explain you why on this slide. If you have an excited atom which enters in the cavity vacuum, after a while the atom will emit a photon, go to the lower state, and you have a photon in the cavity. If the photon can stay in the cavity long enough, it will be reabsorbed by the atom, and you will have a regime of oscillation between these two systems, which is called the vacuum-Rabi oscillation. Quite generally, this oscillation brings the system in a superposition of the state E with 0 photon and G with 1 photon, the amplitudes being the cosine of the sine of omega t, where omega is a Rabi frequency, the fundamental frequency of exchange of energy between the two systems. If you interrupt the coupling when omega t is equal to pi over 2, it's called a pi over 2 pulse, you get to a situation where the atom leaves the cavity and is entangled with the cavity field. You have either an excited atom leaving a cavity empty, superposed with the atom in the lower state and 1 photon inside. The two systems can be separated. It's a non-local entanglement. At that time, in the 1980s, the notion of entanglement was not fashionable as it is today. Of course, we knew that, and we were excited by that, but we were far from understanding all the ramifications of quantum information. So we really wanted to achieve this regime, and I have found here a picture which was taken in Les Ouches in July 1981, where I was discussing with Dan Kleppner, and I want to show this picture because I want just to stress the fact that Dan has been very important for the development of cavity QED, for many ideas, and also for his invention of various techniques that we use to manipulate Rydberg atoms. So on this picture, you see that we were considering already single atom effects, you see, on the blackboard. And also we had the formula for the vacuum Rabi oscillation, but we had not achieved it yet. One of the reasons was that the cavity, it was very hard to improve the Q of the cavity. The niobium was a fine superconductor, but it's a very poor metal to be machined, and the surface of the mirrors were very rough, so the photons were scattered outside. And this order of magnitude that we had to win to achieve this regime was very difficult to obtain. And we were struggling for that until 1984, when we got the news that a competitor, Herbert Walter in Munich, has achieved our Holy Grail. He has realized what he called the micromaser, in which a strong coupling regime was reached. In fact, this was a thesis work of Dieter Meschede, who was working with him at that time, and the system they were studying was quite similar to ours. The only difference was the bright idea to replace the open cavity by a closed cylinder. So even if the niobium had a poor surface quality inside, the photon could not escape. It was just changing a little bit the mode structure, but the lifetime of the photons which were trapped inside the cylinder was very long. So many beautiful experiments have been achieved with the system. It's a system which has been at the heart of many real and also thought experiments. A lot of theorists have been interested in the system, which is useful to demonstrate various fundamental effects in quantum physics. So it's a cylindrical cavity with a very long photon lifetime. So at that time, we thought that we might shift to this kind of cavity, and we even did an experiment on the 2-photon micromaser using this cavity, but we still were not quite happy about that because this cavity had a drawback. The atomic state superpositions are very strongly perturbed by the fact that they have to pass very close to the small holes at the entrance and the exit of the cavity where stray fields perturb the superposition. And moreover, we cannot apply an electric field inside. And to control the Rydberg states and to switch them on and off resonance at will, you need to have an electric field. So we decided to go on with our open cavities. And on this slide, I just summarize the result of 12 years of research to improve the quality of our mirrors. We stick to open structure, to nearly spherical mirrors, but the major improvement came when we replaced niobium by copper, machining the copper with very high precision, having very smooth surfaces, and then sputtering a very thin layer of niobium on top of the copper. And this led us to the improvement that you can see here. The Q of the cavity, which was, you see on the left, you see the quality of the cavity expressed in terms of the number of Rabi oscillation you can do during the lifetime of the photon. And the red line is a boundary for strong coupling. You need to have at least one Rabi oscillation during the cavity damping time. And on the right side, you see the scale of the cavity damping time in milliseconds. So we crossed this boundary sometime in 1995, and we kept improving the quality Q factor until 410 to the 10, which is the best cavity we have now, which keeps the photon for more than 1/10 of a second, which allows thousands of atoms to cross the cavity during the photon damping time. So, and this, of course, has allowed us to perform the experiments I'm going to talk to you about now. You see here the Rabi oscillations that we got in the mid-1990s. You see, this is the probability for an atom to emit and reabsorb periodically a photon. And if you stop halfway between in the middle of this oscillation, you get maximum atom-photon entanglement. And if you make a pi pulse, you convert the energy of the atom into one photon. So you have a deterministic way to prepare photons. And using this kind of Rabi oscillation, we have performed many demonstrations of quantum gates and simple quantum operations that I would not discuss here. The point that I would like to stress is that once you have delivered a photon in the cavity, what we wanted to be able to do is to observe this photon without destroying it. So the question is, how can you detect photons without destroying them? This seems a simple question, but if you think about it, when you look at light, or when you do quantum optics, or just when you observe something with your naked eye, you destroy the photons all the time because you rely on some kind of photoelectric effect. So you get clicks into a detector, but the click means that the photon is dead after it. So the photon dies when it delivers its message, and what we wanted to have instead is a quantum non-demolition situation where you perform a perfect measurement in terms of quantum physics. Once you get a result, you are in the eigenstate of the result. So if you have one photon, you still have one photon afterwards, and you should be able to repeat. This process, in the context of quantum optics, was studied by Vladimir Berginsky back in the 1970s in a different context, and we wanted to achieve that. And for that, we needed a very good detector. These were our Rydberg atoms, and also a very good box to keep the photon for a long time. And this brought us back to this photon Einstein-Bohr box. So this is our photon box, and I said already everything about it. It can keep the photon for a very long time, which means that the photon bounces back and forth for billions of time between the mirrors, and the atoms are crossing this system one by one, and they are destroyed in the end. The atoms are destroyed, but not the photons, because we managed to have a non-absorptive interaction between the atoms and the photons. For that, we need special atoms, not only Rydberg atoms, but the most classical of all Rydberg atoms, which we call the circular one. They are obtained by exciting the valence electron in an alkali, in our case in rubidium, into a circular orbit. And the process by which this excitation is possible using lasers and radio frequencies has been invented by Dan Kleppner and his students back in the 1980s. This atom is very interesting, especially in this year, because it's a realization of the Bohr model. You have an electron going around on the circle, and the quantization is just expressed by the fact that you have an integer number of de Broglie wavelengths around the circle, which is exactly the way that Bohr quantized this. He did not know about the de Broglie wavelengths, but he knew about angular momentum, and the result is the same. So you see that when you prepare such a state, you have no electric dipole, because the system has a symmetry, circular symmetry around the core. But if you want to prepare a dipole, the only thing you have to do is to prepare a state superposition between two nearby Rydberg states, and then the two de Broglie waves will interfere constructively on one side of the orbit and destructively on the other side. You have a big dipole. And this dipole, which is connected to the superposition, will start revolving at the frequency, at the Bohr frequency. And we like to think of this revolving dipole as the hand of a clock. And in fact, what we are building is it's an atomic clock using Rydberg atoms. And this atomic clock is very sensitive to light. Why is it sensitive to light? For that, we come back to the work of my thesis advisor, Claude Cohen-Tanucci, back in the 1960s, discovered the light shifts. The fact that when light is off resonant, it cannot be absorbed or emitted by the atom, but it still modifies the energy levels. When the atom crosses the cavity, their energy is going up or down, depending upon whether you're in state E or in state G. And this results in a phase accumulation of the electric dipole, which depends upon the photon number. You have a phase shift per photon, phi naught, and in circular Rydberg states, this phase shift can be enormous. You can have a phase shift of pi per photon, which means that when the atom leaves the cavity, the dipole will point in opposite direction depending upon whether you have 0 or 1 photon in the cavity. And measuring this phase shift, that is measuring the direction of the dipole, amounts to performing a non-destructive measurement of the photon number. In order to measure a phase shift, you need an interferometer, and so we built a Ramsey interferometer around our photon box. And here this is, of course, the work of Norman Ramsey, who was thesis advisor of both Dave Wineland and Dan Kleppner. So you see the story is a little bit circular here. And we use this Ramsey interferometer as an atomic clock. You see that in the first zone, you have two Ramsey zones, R1 and R2, which are sandwiching the main cavity. In R1, we prepare a superposition of states. It evolves while the atom crosses the cavity. And in R2, we have a second pulse of microwave, which will map the spin, the dipole pointing in one direction back into one energy, E, and the spin pointing in the opposite direction into the other energy state. And in this way, by just measuring the final state of the atom, you will be able to discriminate between 0 and 1 photon. So basically, we have an atomic clock which is delayed by the photons which are trapped inside the clock. Dave, in his talk, will speak about atomic clocks of a different kind. which are about 10 to the 10 times more precise than this one, but they are not sensitive to light. So we are, since we cannot perform high precision physics, we prefer to use this perturbation to do something useful with it, and in our case it is counting photons. And you see the result here. You see this signal which shows how a photon appears and disappears in the cavity using this technique to detect it. And you see that you can observe the quantum jump of the cavity field going from 0 to 1 photon. You also see that hundreds of atoms see the same photon, so it's really non-destructive. And this is, we did many tests of this experiment. We can also count larger photon numbers. For that, what we do is that instead of sending only one atom, we send a sequence of atoms. And you see here histograms evolving as you get information after many atoms have crossed the cavity. And you see that at the beginning, you don't know what the photon number is. You have a flat histogram. And as atoms get detected, you can update your knowledge about the field, and eventually, in one realization, here we find 5 photons, in another one we find 7 photons. And you get a very important, a very basic result here, which is of course well known, is that quantum physics is random. When you start the experiment, if you have a superposition of many photon number states, you don't know which one you will get until you have finished the experiment. We have also able to observe quantum jumps with many photons. You see here a kind of staircase evolution of a field going down from 4 photons or from 7 photons back to vacuum. And again, you have the randomness of quantum physics, which is, of course, obvious here. You can also, once you have detected the signal, use the detection to feed back onto your system and to stabilize the system for a given photon number. Here you see that we have been able to stabilize up to 7 photons in the cavity using this feedback method, which I don't have time to discuss, but it was a topic of Michel Bohn's talk in one of the sessions this morning. So at this point, I have emphasized the fact that light is made of particles, because I have been talking mainly about photons. But as I said in the beginning, light is also a wave. So depending upon when you look at it, it's either a particle or wave. And now I would like to finish by experiments which stress the wave aspect of light. And of course, the most wavy light you can think of is a coherent state, a state of radiation which is classical. And I will show to you that it's possible to combine coherent state to build equivalent of Schrödinger cats, superposition states involving many photons. And this is a topic that we have been studying for many years. So I come back to a coherent state of light. A coherent state of light is just a wave oscillating with a given amplitude and phase. So you have 2 important characteristics of the light, which is the amplitude and the phase. And you see here, for instance, 3 waves which have the same amplitude but different phases. They reach their maximum at different times. And it is well known, all engineers and physicists know that to represent a wave, you can use a C number or a vector whose amplitude length is the amplitude and whose direction gives the phase. For example, the 3 waves here are represented by 3 vectors at 120 degrees from each other. If you go to the quantum description, the only thing you have to add is quantum uncertainty. The tip of your vector will become fuzzy, and the distribution of the tips is given by a Gaussian function. A coherent state has a fuzzy tip around an average value, and this distribution accounts for the uncertainty in the photon number in the axial direction, and uncertainty in phase in the angular direction. So this is what a coherent state is about. How can you prepare a superposition of coherent state? We made this proposal about 20 years ago in a paper published with our Brazilian friends and colleagues, Luis Davidovich and Nissim Zaghuri. And we discussed in this paper the fact that we could, with a single atom, transform a coherent state into a superposition of coherent state with different phases. And we said in the end of the paper that this was realistic with Rydberg atoms and very high Q microwave cavities, and that the possibility of photon manipulation through non-resonant atom field interactions opens a domain in cavity QED studies. And I just want to stress what we did is to transform, to change with a single atom a coherent state into a superposition of two coherent states, one which we can call the live cat and the other the dead cat. And in its Wigner function, it's no longer a Gaussian. In between the two Gaussian peaks, you have fringes which reveal the superposition, the fact that we have a superposition which can give rise to interference effects. And we also reminded in the paper the fact that if you prepare such a superposition, if you wait, the superposition is very fragile. In a very short time, it is transformed into a statistical mixture in which the interferences have disappeared, and of course this is decoherence. So we made this proposal in 1991, and you see it took us something like 15 years to implement it really in the way that I will discuss now. So it's a really long-term project because we had to make technological advances and learn to manipulate the system better and better. How do we prepare a Schrödinger cat? Again, the Ramsey interferometer. We start with a coherent field in the cavity, and we send a single atom, and just before it enters the cavity, we apply a pulse which prepares superposition of two states, E and G. And this superposition crosses the cavity, and the two states impart different phase shifts to the field because they correspond to different refractive index for the field in the cavity. It's again a dispersive effect. So after the atom has left the cavity, you have a superposition of two combined atom field states. The atom in one state is correlated to the field having one phase, and the atom in the other state, the field has another phase. This is an entangled state, and it is something which is reminiscent of the Schrödinger's cat, as I will tell you in a moment. Now, there is another thing you have to do if you want to keep the quantum ambiguity. It is to mix the levels again in the second Ramsey zone. This means that when you detect the atom after, you have no means to know in which state the atom was when it crossed the cavity, and the field collapses into a superposition of coherent states with different phases. Once you have prepared the Schrödinger cat, you have to measure it. And for that, we need another trick. But first of all, why do you call that a Schrödinger cat? Of course, I remind you the story of Schrödinger. You have a single atom in a box. The atom can be in two different states. In one state, the cat is alive. In the other state, it triggers a device which kills the cat. And you have a superposition. In our case, in our version, we have the cat is replaced by an ensemble of photons, but you still have a single atom. And depending upon the state of this single atom, the fate of the state superposition for the field is different. Once you have prepared the cat, you send other atoms across the cavity, and you use a modified version of the QND measurement to reconstruct the Wigner function of your cat, and you get the following result. So you have two coherent states with different phases. You see the coherent components of the cat, and you also see the quantum interferences in between. And once you have the Schrödinger cat, you can perform decoherence studies. In order to study the fragility of this cat, you just prepare it, you wait for some time, and then you reconstruct the Wigner function, and you change the delay. And in this way, you can realize a movie of decoherence as it processes. The theorist which has popularized this idea of decoherence in this context is Wojciech Zurek, and we followed his ideas to make the theory of our experiment. I will just show you in this movie, and this will be more or less the end. You will see how, as a function of time, the fringes disappear, they get blurred, and they disappear very quickly. And we made many studies of this phenomenon, which shows that decoherence destroys quantum coherences much before it damps the energy of the system. We made an earlier version of this experiment about 15 years ago, but at that time we were not able to reconstruct fully the Wigner function of the system. So I think it's time to conclude. I would like to connect now this physics with things which have been being done in other labs. Our Rydberg atom with microwave in superconducting cavities is somewhat related to cavity QED in the optical domain, using cold atoms interacting with optical microscopic cavities. And Jeff Kimball and Gerhard Rempe have been pioneering in this field. You can also replace the cavities by whispering gallery mode of microspheres or microtoroid resonators. You can do it also in solid-state physics using quantum dots replacing the atoms and Bragg structures or photonic band gaps for the cavities. And a field which is expanding very rapidly now is a field of circuit QED, in which the atoms are replaced by Josephson circuits, and the cavities can be either 1D, 2D, or now even 3D superconducting or metallic cavities. And this system has been developed in many, many laboratories. You have a lot of sessions in this APS meeting devoted to that. And I think it's fascinating because the ideas are very similar. The systems are different, but the Hamiltonian, the coupling is the same, with a big difference that these huge atoms, these atoms are even much bigger than the Rydberg atoms, and the coupling, the Rabi frequencies are orders of magnitude larger, which makes a lot of things easier than with Rydberg atoms. Just to show you the analogy I show you here, again, our Schrödinger cat compared to a cat that had been obtained recently at Yale University using a similar, using a somewhat different physical effect. You have had also Schrödinger cats, which have been realized in Santa Barbara in the group of John Martinis. And I think this physics is really fascinating. And if you have application for quantum information, it's more likely to come from solid-state devices that you can reproduce with well-known techniques, and you will never have a quantum computer with Rydberg atom flying around in an atomic beam. So what kind of application? I will leave this question open for Dave to answer. And I would like just to acknowledge my co-workers. Of course, this has been, I have discussed already in the talk, it has been a very long-term work. And I've been very lucky to be able to collaborate over all these years with Jean-Michel Raymond and Michel Brune, and Michel is here today. We have had a lot of other colleagues, postdoc and friends coming from all over the world, and I see some of them here around also. And I want to finish by acknowledging the atmosphere, which was very conducive to this kind of research, allowing us to work on the long term without having to report every year about the result or the promises of improbable applications. And this has been possible in the Kastler-Brossel laboratory following the spirit that Kastler and Brossel have imparted to this lab for a very, very long time. I have been lucky to be there about 50 years ago when Kastler got a Nobel Prize in 1966. So you see on this picture Claude, Kastler, and I am on the other side. This picture was taken in the room where we are now working 46 years ago. And I will finish with that picture, and thank you for your attention.
Thank you for a beautiful talk, and we now have time for some questions. I hope we have a roaming microphone that we can use to this end. Yes, sir. Why don't you stand up so we can hear you?
Which next groundbreaking experiment would you suggest for the next Nobel Prize?
I will pass.
The question was which next groundbreaking experiment would be suggested for the next Nobel Prize?
You have a lot of groundbreaking possibilities in all kinds of fields, so I cannot answer that question, but there are very exciting things going on in all domains, as you can see from the audience here.
Other questions, please. We have a few minutes for questions. If you'd like to ask a question, why don't you stand up so I can see you?
Yes.
Yes, sir. When do you think there will be a practical quantum computer?
I think I'm not the right person to be asked this question because I am very skeptical about the fact that there will be a computer, an all-purpose quantum computer, because of the huge difficulties. Decoherence, quantum error corrections are are extremely difficult to implement. But what I am sure that there will be applications. Simulators using an ensemble of ions or atoms in optical lattices are already around, and they're already on the verge of being able to do things that classical computer cannot do. So I don't think this will be interesting for the general public who would like to have a computer at home, but for us physicists, it's certainly very, very interesting. And moreover, I think that there will be applications that we cannot even think about today. As you know, if you take the example of the laser or of magnetic resonance, the people who invented them would never have guessed what would be the applications. And I'm sure it will be the same for what we are doing now.
On that theme, would you care to speculate on how large of a Schrödinger cat do you think we can reach eventually?
I think that some people here are doing larger cats with you have reached 100 particles or something. How much? 111, okay. So you see, you can, at some point, decoherence becomes a problem, because the larger the cat is, the faster decoherence, and the longer it takes to build a cat. So at some point you get into a problem, but it's amazing what you can do now would not have been guessed 10 years ago.
More questions from the audience, please. Yes, sir. Yes, sir.
So you talked about the importance of decoherence just now.
Yeah.
And can you give us some sense of what one has learned about decoherence? For the non-specialist, this just seems to be a sort of magical word, and I put it along with friction and all those other things, and things doesn't really explain on a basic sense. So it would be helpful, I think, if you could give us some sense of what you learned about coherence, the source of coherence, and the methods you fought against it.
It's a very important and interesting topic, but very difficult to answer in a couple of minutes. It's clear the kind of decoherence I'm talking about is a decoherence which is produced by the environment. The fact that you have a system which leaks information into a reservoir, a bath, and this loss of information into the bath destroys the interfering properties of the system. And this is exactly what you have in all complementarity experiment. You see interferences as long as you cannot find out through which path the system went. And so this is what decoherence is at this level. Of course, some people believe that there is something which is less mundane than what I am talking about, that there is a fundamental process which should at some scale destroy superposition states, but nobody knows if this exists or not. And certainly the experiments that we are doing are not checking that, or testing that. And if we see that decoherence does not proceed as we expect, we will first suspect that there is something wrong with our experiment before finding something at fault with quantum physics. In principle, quantum physics should stand at all scales, and in this sense, there is no fundamental decoherence. The decoherence is just the fact that we are not able to follow all the quantum correlations. You have to focus your attention on the subsystem and to forget about the information leaking outside. And this idea, it seems simple, but until about 20, 25 years ago, this was not so clear. And I think Wojciech Zurek and all the people who have been working, Anthony Leggett, all the people who have been working in this area have helped very much clarifying this. And the new thing is now that we can do experiments to test these ideas.
There was another question over there.
Yeah. What was the question?
Are there outstanding questions in the foundations of quantum mechanics that can be addressed in these experiments?
I think one outstanding question is what I just said. Is it clear that quantum superposition should stand at all scales? Can you imagine an experiment in which you will find a process different from the one we are talking about here? Some people think, I think Anthony Leggett thinks around these lines, and I think it has been a triggering factor in the development of superconducting qubits. In the 1980s, the first ideas came out because one wanted to make sure that one tried to build a quantum system, a large quantum system, and see whether quantum physics applied to them, and apparently it does. So there is the frontier where quantum physics stops to be valid is not, there is no frontier for the time being.
A while ago, you wrote an interesting paper in Physics Today with a provocative title, Quantum Computing Dream or Nightmare. You did address this.
Yes,
but,
so that's why I said I was not the right person to answer. I said in this paper that it was a dream of theorists, and I think it's very important because theorists really have thought deeply about this question, about the complexity of quantum system, about the possibility to correct errors, and this has been a tremendous breakthrough. On the experimental side, it's still a nightmare because you have to try to control a huge number of particles. I know that Dave does not, Dave, I think we agree, maybe not in the wording, but after my paper came out of Physics Today, Dave sent a letter, and I replied to this letter. And at that time, I remember I said, I think in 10 or 15 years from now, you will be able to juggle with 5 to 10 ions in a trap, and this will be fantastic, but this will be far from a quantum computer. And I think we are still there now, but I cannot say never, I don't know. I think something interesting will come out, whether it will be a computer or not, I cannot tell.
On this optimistic note, why don't we thank Serge again for a beautiful talk.